Hey, today we have the fundamental theorem of calculus, which explains the relationship between indefinite integrals and definite integrals. Here I have a function f of a variable that I'm calling t for reasons that will become apparent very soon. You see I've labeled this axis the t-axis. And the reason is that I'd like x to be a variable between a and b, so you can see I have x down here. It's some point between a and b. And now I would like to define this function capital F of x to be the definite integral from a to x of the function f of t with respect to t. Which is to say that capital F of x is the area under the curve from a to x. Now, I said that x could be any value between a and b, and if x is precisely equal to a, then capital F of a is the area under the curve from a to a, or the definite integral from a to a of this function little f of t, and that's clearly equal to 0. On the other hand, if x is equal to b, then capital F of b is the full area under the curve from a all the way to b. It will ultimately be useful for us to write the area under the curve from a to b, or the definite integral from a to b, as capital F of b minus capital F of a. And since capital F of a is 0, and capital F of b is the full area under the curve from a to b, then we can certainly do this, because this is the area under the curve minus 0. So capital F of b minus capital F of a, the area under the curve from a to b, or the definite integral from a to b of this function f. Okay, here's where the fun begins. Let h be some small value, like for example the distance from here to there, call that h, and consider capital F of x plus h. That's the area under the curve from a to x plus h. And subtract capital F of x, the area under the curve from a to x, and what you get is the shaded region that we have here. And it's not quite a rectangle because it's got this curved section at the top, but it's nearly rectangular. It's at least approximately rectangular in the way that we approximated areas under the curve using Riemann sums. And if we wanted to do exactly that, use the same techniques that we used with Riemann sums to try to approximate the area of this shaded region right here, well, then we could use left endpoints, right endpoints, midpoints, some other points. But if we used left endpoints to construct a rectangle out of this shape, then its width would just be the distance h right here, and its height would be the height at the left endpoint, which is f of x. And so width times height, h times f of x, that's an approximation for the area under the curve there, which is capital F of x plus h minus capital F of x. Okay, we have capital F of x plus h minus capital F of x, which is the area that was shaded in the picture we were just looking at, is approximately equal to h times f of x. Dividing both sides by h, we get this expression here. And then the key idea is the same idea that we had with our Riemann sums, or when we developed definite integrals, is that the more rectangles you take, or the thinner you make the rectangles, meaning the smaller you make this value of h, the closer and better the approximation becomes. So that if you let the number of rectangles go to infinity in the Riemann sum case, or in this case, if you let the width of the rectangle or the distance h go to 0, you get no longer an approximation, but an equality. So we have the limit as h approaches 0, of capital F of x plus h minus capital F of x all over h, precisely equal to f of x. And that, of course, gives us the punchline that the derivative of this function, capital F, is precisely equal to the function lowercase f. And what we have just done is proven the first part of the fundamental theorem of calculus. It says, suppose you have a continuous function on a closed interval from a to b, and suppose we define this function capital F the way we did before to be the area under the curve from a to some point x. So we define capital F of x that way. Then it turns out that the derivative of capital F is equal to lowercase f, or another way of putting it, capital F is an antiderivative of lowercase f. Okay, like we just said, capital F is an antiderivative of lowercase f, but we also said while we were working this out that capital F of b minus capital F of a is equal to the definite integral from a to b of the function f of t dt, but with the t is just a letter, you could just as well write f of x dx. Which brings us to the second part of the fundamental theorem of calculus, which says that if we have a continuous function lowercase f on a closed interval ab, and capital F is any antiderivative of lowercase f, then the definite integral from a to b of f of x with respect to x is capital F of b minus capital F of a. This we have not yet proven. Well, in particular, what we've proven is that for the particular antiderivative, capital F, which was this area from a to x function, this works. But what we haven't yet shown is that it works for any antiderivative of lowercase f. But it turns out it is actually very easy to prove that that's the case. Suppose you have a different antiderivative, capital G of x, an antiderivative of lowercase f. Well, when we were looking at the mean value theorem, one of the corollaries was that if two different functions had the same derivative, meaning they were both antiderivatives of the same function, then they must differ by a constant. So if g is an antiderivative of lowercase f, like capital F is, then capital G is equal to capital F plus some constant. And then you can see, what is g of b minus g of a? Well, it's capital F of b plus a constant minus capital F of a plus a constant, and the constants cancel, and you just get the exact same value, capital F of b minus capital F of a. Let's look at an example. The definite integral from 5 to 7 of x minus 2 with respect to x. And I choose this example because we've already looked at this example when we first studied definite integrals. We computed this definite integral just using geometry. And using geometry, we found that the definite integral was actually equal to 8. We should get the same answer when we do it using the fundamental theorem of calculus part 2. And the fundamental theorem of calculus part 2 says we first start with any antiderivative of x minus 2. Well, here's one. Capital F of x equals 1/2 x squared minus 2x is an antiderivative of x minus 2. It's easy to check. Take the derivative of this, you'll get x minus 2. Notice I didn't add the plus c. The plus c, when you're taking an indefinite integral or trying to find the general solution, all the antiderivatives of x minus 2, that's an infinite family of functions, but I only need one. Since any antiderivative will do, I may as well take the one where the constant c is equal to 0, just to try to make the arithmetic a little bit easier. And the fundamental theorem of calculus part 2 says that this definite integral is equal to capital F of 7 minus capital F of 5, which is 1/2 times 7 squared minus 2 times 7 minus the entire quantity 1/2 times 5 squared minus 2 times 5. Notice that those outer parentheses are absolutely needed because you have to subtract all of capital F of 5. And the arithmetic is not so interesting, but you have to grind your way through it. And when you get to the end, you see that the answer is indeed 8, just like we found geometrically in a different video. It's a little awkward having to go off on the side like this and come up with this function capital F in order to compute the antiderivative. And it would help if we had some notation that might make this simpler and more elegant. And we do. It's this notation down at the bottom here. It's that capital F of x evaluated from a to b, that's how you pronounce this thing right here, is just equal to capital F of b minus capital F of a. So we will be using this notation to mean this. And look at what that lets us do. That lets us start with the definite integral right here and go straight to this step right here without having to invent some new function name. We just take the antiderivative and write it evaluated from 5 to 7. Which means the same thing that it did over on the right. We plug in 7 first, and we get 1/2 times 7 squared minus 2 times 7. And then we subtract the entire quantity, 1/2 times 5 squared minus 2 times 5. And of course, the same arithmetic yields the same result. We get that this definite integral is equal to 8. I'd like to do one more example, the definite integral from 0 to 2 of x squared plus 1 with respect to x. And the beauty of this example is that the answer will give us the precise area under the curve x squared plus 1 from 0 to 2. This is the area that we were trying to approximate with Riemann sums when we studied Riemann sums. Taking the antiderivative, I find that the antiderivative of x squared plus 1 is 1/3 x cubed plus x. So this definite integral is equal to 1/3 x cubed plus x evaluated from 0 to 2. And that's just notation for 1/3 times 2 cubed plus 2 minus the quantity 1/3 times 0 cubed plus 0, which, after you do the arithmetic, simplifies to 14/3. So the area under the curve x squared plus 1 from 0 to 2 is 14/3. Okay, that was the fundamental theorem of calculus. We focused mostly on part 2 of that fundamental theorem, which gives us a practical technique for computing definite integrals using indefinite integrals or antiderivatives. There's a homework on that with lots and lots of practice. Before we say goodbye, I'd like to say a quick word about part 1, just to show you some of the coolness that arises there. So here we go. Just to quickly refresh our memory, part 1 says that if we define this functional capital F of x to be the area under the curve, or the integral from a to x of some function f of a variable t, then capital F is an antiderivative of lowercase f, or the derivative of capital F is lowercase f. Well, here's an example from physics. It's the Fresnel function. A Fresnel lens is one that focuses light using diffraction. The Fresnel function is defined as capital S of x is equal to the integral from 0 to x of the sine of pi times t squared over 2 with respect to t. And suppose that you're working on some physics problem, some optics problem, and you're given the Fresnel function and you need its derivative. Well, couldn't be easier. This is what the fundamental theorem of calculus part 1 says. It says that its derivative is just the function that you're integrating. So capital S prime of x, the sine of pi x squared over 2, done. I had no more work to do. Okay, that was both parts of the fundamental theorem of calculus. The part 1 we won't use that much. You won't see it on your homework. It comes up every now and then on standardized exams. They like to show it to you because it looks scary, but it's really quite simple. Anyway, have fun with your homework. Look forward to seeing you in class.